Hi everyone, I'm Won-Lee. I'm going to explain random variable x, which plays an important role in statistics, and its probability distribution function, f of x. Okay, let's see. Random variable and its probability distribution function, f of x. To expand the sample space what? The whole outcome of an experiment. Sometimes it's can be described by some signal, not a real number. So from sample space to say population usually consists of real numbers. We define random variable x is a function that transforms each subset of the sample space into real number, okay? Therefore, sample space becomes what? Population, composed of real numbers. Okay, probability P dot is defined over sample space. And since the sample space becomes a population through a random variable, the probability defined over population becomes the probability of random variable x. That is expressed as usually f of x. Okay, sample space here. And random variable x is a function which transforms subset of a sample space to what? Real number. Okay, that is population. So we may use x as a population. Then there is a probability p dot. Okay, then there is also a probability f of x over population. Okay, that's why we understand random variable x and its probability distribution function f of x. Simple example, assume tossing a coin because it is very simple. Sample space consists of h and t, head and tail, right? Probability defined on sample space like this. P of h is 0.5, P of t is 0.5, okay? That's it. When we studied probability, this one is a simple example, and this is probability. These are probabilities. Let x be the number of heads. Then x takes values 0, 1, 1. When head, then x will take 1. When tail, then x will be 0. X will take 0, right? So f of 0 equal to 0.5, f of 1 is also 0.5. Here is a simple example. Statistics is developed using random variables. We will study random variable now, from now on, only random variable and its probability distribution function, f of x. That's it, all right? Simple. Uh, Classification of a population, classification of x. First, random variable x may be broadly classified into discrete and continuous types based on the data in the population. That is, when x takes an countable values, x takes countable values. Countable means count with your fingers. It is referred to as discrete. And the other case, otherwise, it can be referred to be continuous. Okay? Example, discrete, face number of die, 1, 2, 3, 4, 5, 6. There are only 6 numbers. Okay, that is discrete. Satisfaction level on a 5-point scale in a survey. Very dissatisfied takes 1. Satisfied 2. Neutral 3. Satisfied 4. Very satisfied 5. Then this kind of a random variable or population is discrete. Okay, but sometimes statistician treat it as continuous. It is some deep thing. So you don't have to know it right now. Scores of 100 questions, multiple choice exam. Then x takes 0, okay, 1 to 100. So this is like discrete, but many cases, we consider it as continuous. It is appropriate to consider it as continuous. Okay, there are 101 values, from 0 to 100, so 101, so countable. So somebody, especially beginners, consider it as discrete, but this kind of a thing, this kind of data, this kind of a random variable, we consider it as continuous. Car speed, temperature, height, fees, that kind of thing, these are naturally continuous variables. Okay, so it just depends on scale. Okay, how to temperature 0, 1, 2, 3, something like integer values, then looks like discrete. But this is integer values of a temperature is what? For convenience. So there is 1.2 degree, 2.7 degree, something like that. It is also possible. So we consider it, this kind of data, continuous, like here. Okay, it is a multiple choice exam. Multiple choice exam is for convenience to make scores. But some people, uh, some people may score like 0 to 100. Here, this is 20.126. Okay, something like this. Exam scores like this, but multiple choice exam is for continuous, to score fast or for convenience. So you may consider it as continuous. It is a little some complicated thing, delicate thing. Data X can be classified by scales as follows. Nominal scale. This is the scale in which numbers are assigned for purpose of classifying or identifying the characteristics of measured subject. For example, gender, religion, occupation. It cannot be measured like a number, real number. Okay, classified, classified things, and judge number of athlete. That kind of thing is we call nominal scale. Ordinal scale. This scale indicates the order of a relationship among measured subjects. For example, living standard, high, medium, low. Quality ratings, preference rankings, or grades, A, B, C, D, F. That kind of a thing we call ordinal scale. Interval scale. This refers to a scale that assigns lengths to the attributes of a measured subject with equal intervals between the lengths. For example, survey questions such as one very satisfied, dissatisfied, neutral, satisfied, very satisfied. That kind of thing is called interval scale. Ratio scale. This is a scale for data that allows for the comparison of an absolute magnitude. We will consider the data such like ratio scales, say real numbers. Okay. Okay. Definition of a probability distribution function f of x. For discrete random variable, they say probability mass function. For continuous random variable, somebody say probability, excuse me, density function. But I think we don't have to distinguish the what terminology of mass and density, the same thing. Let's express probability distribution function of a random variable x as f of x. Okay, whether x is discrete or continuous. Random variable x follows a certain probability distribution function f of x. There is a random variable, then that random variable has a certain probability distribution function. It can be said x has a probability distribution f of x. In this case, if it is f of x is probability distribution, then f of x must satisfy following condition, like when we say probability. probability. F of x takes greater than equal to 0 for all x. F of x cannot be what? Negative. It is the value of f of x anyway is non-negative. For discrete random variable x, sum of x, all x, of course, all x, f of x is equal to 1.0. For continuous random variable, integral of f of x is 1.0. What this means in integration means the area under the curve. Under the curve means under the fx. Okay, such like this. The integration, okay, means area under the curve, like this. You may understand, or even though you don't understand integration, no problem to follow this course, this level course. So I show one example histogram, relative histogram, relative frequency histogram like this. Then the sum of heights means 8.5 plus 13.4, 28.4 plus up to 9.8. This should be 1.0. In other words, 100%. Okay? When it is treated as discrete. But when same data, we consider it as continuous, then the total area under the curve, this one should be 1.0. I told this kind of thing previously when we studied histograms, right? So I told you sometimes this kind of thing, scores of 100%, 100 question, multiple choice exam, this question, if you consider it as discrete, then sum of this height should be 1.0 or 100%. But when you consider it as continuous, then the area under the curve is 1.0. Can you get it? Okay? Please, I think you may understand that kind of thing. Okay? Definition of f of x. It is important, of course, natural thing. And you just started to get in statistics, I think. Okay, that's it today. Bye.